Okay, here we are. We're going to perform a little test, figure out how much stiffness this white line sway bar adds. Also measure some other stuff too. And the first step to do this is to figure out what the free length is, a convenient measuring point without the shocks attached. Because once you bolt the shocks in, you're going to have a bunch of preload that holds the springs compressed, so we need to figure out what the free length is. That way we can compare how much load is transferred through the sway bar or through the original twist beam, and then with the addition of the sway bar. So here I've got jacked up on stands, and I've got the shocks unbolted, and I've got it drop down enough that the spring just comes unseated at the top. And we measure to the body. From the body down to the wheel, 263 millimeters. Now we'll bolt those shocks back up, and then we'll figure out what the difference is in height there, and that'll be the preload. Okay, now we've got the left side shock bolted back in, and that's going to show us what the kind of preload, the amount of preload that's on the spring there. I've left the right side disconnected. That way when we do our test and see how much load is transferred through the beam and the twist bar, we're not constrained at all by the preload, and the right side will just move however much it needs to.
Hey, are those like you?
And the left side here, we're at 210 millimeters.
Yeah.
Okay, now we've got the cars off the jack stands, completely supported by the left side. Right side's off the ground there. And the left, or the right shock rather, is still disconnected. Now we're going to come around and measure at about 210. So that's pretty much what we figured what the preload was too. So that's with the sway bar connected. With the sway bar disconnected, we'll find that number will be kind of within the range of the free length to the preload. So it's a good thing we just left it disconnected. Okay, here we are with the sway bar disconnected, right there on the ground. Left side jacked up, right side not touching the ground, just makes it. And now we're looking at 223. Okay, here we are. So it's 223 millimeters without the sway bar. It's 210 with the sway bar. 210 millimeters on the droop with if the shocks were bolted in, and the free length was 263. So you can see a little bit of basic math there. The sway bar increases the force by 32.5%. Fairly significant. So after posting the results, I thought about it a little more, and I realized that I had forgot something, and that there was a correction that I needed to make. So on the sake of accuracy, I repeated it, and what I had forgot to do was measure the values for the left hand side. So as I jacked up the left hand side, basically what we did for the test was, here's the twist beam. We jacked up the left-hand side, and then we measured the force using the spring deflection on the right-hand side. And we know because we know the difference between the heights left and right, we can use that with the spring constant for the axle against the deflection of the spring from the free length to the compressed length, and the spring constant for the spring. And when those forces equate, and when you figure them out, you end up with this. You end up with 114, that's millimeters, and that's the spring constant for the axle, equals 40 millimeters times the spring constant for the actual spring. And then with the sway bar, you've got 105 with the axle. The spring constant of the axle plus the sway bar is equal to 53 millimeters times the spring constant of the spring. And when you divide the two of them, you end up with this correction factor that I had left out in the original. And so you actually end up with that the sway bar adds 44% stiffness over the original twist beam axle. Also, if you're interested, here's the sway bar, 7¼ pounds. Not that heavy, and because it's offset and the rear axle is actually pivoting around the bushings, puts the bulk of the weight of the sway bar closer to the pivots, so the effective increase in unsprung rotational inertia is not quite that much.